So we're going to go ahead and do our next video on refraction. The last video we did was on reflection, and this one's going to be a little bit longer than the reflection one was. We've got a little bit more to do with it. So let's get started. So the first thing I want to think about is this is dealing with an object that is moving, an object specifically, a wave that's moving, and it changes mediums. It goes from one medium to another. And to kind of give you an idea on what will happen, I want to think about rolling a barrel across a border from something that it would roll fast on to something that would roll slow on. So what we're going to do is go ahead and put, like here, this is going to be just some grassy area. And so this will be grass down here, and up here it'll be concrete. Okay? And so something's going to roll a lot faster on the concrete than it will on the grass. And what we're going to do is we're going to have a barrel, right? My great barrel right here. Okay? And this barrel is going to roll down towards the concrete following this path, right? And then when it hits the grass, what's happening is when it's rolling on the concrete, this side and this other side, they're going at the same speed. So this rolls in a straight line, straight down this way. But when it reaches the grass and the barrel starts to hit the grass, it only hits it on one side first if it's coming in at an angle like this. And so what that's going to do is it's going to cause this side over here that hits the grass first to slow down while this side over here is still going fast. And if you think about what will happen at that point, it means that this side over here is going to actually move out ahead of the side that hit the grass first. And if that happens, it's going to cause the path of this not to go in the straight line that it would have gone in, not to come out, not to come out straight this way, but rather to curve its path and come over this way. So the barrel will end up rolling along a deflected path as it goes over this way. And vice versa, if we did it the other way, here's our grassy line here. If we sent the barrel the other way from the grass, so here's our barrel, okay, there's our barrel, and it's rolling along this path here, okay, and then it hits the grass. When it hits the concrete, I'm sorry, the side that's going concrete over here, both the sides are slow. But when we get over here, the side that's still on the grass is going to be going slow, and the side that leaves and gets on the concrete can start to speed up. And when that happens again, this side's going to speed up, and it's going to get ahead, the side that's going faster, the side that's on the concrete, of this side. And what this is going to do is instead of this going off in a straight line this way, it's going to cause it to bend and go out this way. Okay? And so whenever this goes from something that it's going fast in, that's the concrete, so the concrete is fast and the grass is slow, it's going to deflect. It's going to make it change paths. And light is going to do the same thing. It's going to do something just like that. Not just light, but really any wave, but we're mostly interested in light doing this. And if we draw in a normal line being perpendicular, something normal, it's perpendicular to this boundary. So here's the grass concrete boundary, and we draw a line in perpendicular like this. What we can see is that this is the angle it went in at. We're going to call that theta I for incident angle. And then this over here is the angle this is called refraction, theta R, that it refracted to when we do this for light. And the same thing over here. If we draw in this normal line, perpendicular to the surface, here's our incident angle, and here's our refracted angle, what it bent to. And in this situation, where it went from fast speed to low speed, we can see that theta I is greater than theta R, which means that it bent in a way that it bent towards the normal. Like this is the path it was going to be on, but it bent over that way, toward this normal line. Over here you can see that theta I is less than theta R, which means it bent away from the normal. So here's the path it was going on, and it bent away from that normal, bent over this away from it. And so that's our two main situations. And we do something pretty much identical for light. If we draw in a boundary, say this is air, where light moves fast, and over here This is glass, where light moves more slowly. If we draw in a normal line, just like before, and I'm going to use red for the light rays, we can have a light ray coming in at some angle. Okay, here's our light ray. This air is fast, and this is slow for light. Okay, which means it's going to follow what the barrel did. Fast to slow, it's going to bend toward the normal. So it's going to bend over here, and it's going to get closer to that normal. So this would be theta I, this would be theta R, and here theta I is greater than theta R. It bent towards the normal. We can come over here and draw another one of these, draw our same air to glass boundary, still air, glass. So this is fast, this is slow. And we can draw in this normal. And then the light ray, we can send in the other way. The light ray can come in this way. So send it in about a 45-degree angle again. And it will bend away from the normal. So it's going to bend over away, getting to a greater angle. And again, this is the incident angle, theta I. This is the refracted angle, theta R. And just like in the barrel example, the incident angle is less than that refracted angle, bent away from the normal. So you can model and kind of think in your head, what is light going to do, just by thinking about what would the barrel do, going from a fast surface to a slow surface, or a slow surface to a fast surface. Light's going to do the same thing. So as long as you know which medium that the light is faster in, then you're going to be able to figure out which way it will bend, either toward or away from the normal. So that's all well and good. That just tells us toward and away. What we want to be able to do is develop a method for figuring out what these actual angles will be. So say if you knew what angle it was coming in at, what angle would it refract to? And to do that, we first need to define the index of refraction. This is essentially a number that will allow us to quantize what the optical density is, as it's called, the optical density. And this is based on the index of refraction. Index of refraction. The bigger the index of refraction, the more optically dense the medium is said to be. We're going to represent this with a lowercase n, okay? And we're going to do this as the speed of light in a vacuum divided by, all right, speed of light in a vacuum divided by, right, so divided by the speed of light in the medium. So if you have a medium, right, that's divided by, if you have a medium where the speed of light is cut in half, so say it goes through some material that you have and it slows down to half of what it is in the universal constant speed of light in a vacuum, then you're going to have an index of refraction of 2. Okay, because it'll be speed of light divided by half the speed of light. So you get 2. You should notice that the faster, so well, let's put it this way, the faster light is in the medium, the faster light is in that medium, that gives you, and we can say it's back and forth, gives you the bigger n, and the slower light is, gives you a smaller n. So basically what you're seeing from this, what I'm trying to tell you to take note of, is that the speed of it in the medium, how fast it is inversely proportional to n. The bigger n is, the slower light goes in it. The smaller n is, the bigger the speed is. So up here, when we said this is fast, this means small n. Down here, this means big N. And so we could call this the index of refraction of the incident material in I, that's this one, so I could put a little I there, versus the index of refraction of the refracting material right there, that it's going to be the opposite, it's going to be in R. So, and then we can say, if we wanted, I guess we could write VI, the speed in the incident material, is bigger than V refracting material. And then over here is the opposite. This is fast, so it's the big, wait, I'm sorry, it's still the, what am I doing? I'm trying to write the opposite of what I see here instead of thinking. This is the small n, same thing, but now this is the refracting material, and here this is the big N, and it's the incident material. So when we look over here now, in I is greater than in R, and you also have that VI is less than VR. Okay? So just kind of keep that in mind. And again, if you can think your way through the barrel thing, if you can think your way to which way would a barrel bend, and you can remember that a big index for refraction means a slow speed, then all of this that we have right here for light, you can figure this all out. You don't have to worry about memorizing all these properties. You should be able to think your way through it, much like I just kind of talked you through being able to do it. Okay, so that's our first part. We have to define the index of refraction. Now, what good is it? Well, it turns out it's pretty good through something called Snell's law. And there's a couple different ways you will see it. I think in your data booklet you're going to get one version. I usually like to write it this way: in I sine theta I equals in R sine theta R. And so that's the way I remember it. In your data booklet, I believe you're given N1 over N2, and I would just say 1 is the incident and 2 is the refracted, so like this is the first material it's in, this is the second material it's in, is equal to, and if you look at this, we just divide NR over and divide sine theta over, this would be sine of theta 2, so that's the refracted angle, over sine of theta 1, that's the incident angle, I wrote I, but 1. And then if you look at this little version here, it would be V, the speed in the second material, the refracting material, over the speed in the first material. Okay, and this is what you're actually given in your data booklet, and it's kind of a mixture of the Snell's law like this and this put together, and that's ends up basically what you have. So the only thing you really have to do at this point is, I could give you a problem, or you could get a problem or something that says this is the angle of incidence and it's going in this material, it refracts to this other angle, what's the index of refraction of the material that it went into? So you could say, all right, well, like over here, I know this is air, it has an index of refraction of about 1, I think it's like n equals 1.003, very, very close. If you'll notice, this has no units, of course, because this is a speed divided by a speed. It's just a ratio. So it's 1.003. For a vacuum, it'd be C over C. It'd be exactly 1. So even in air, it's pretty close. And as this light would come in, it would bend over, and you could measure this angle you sent it in at and the angle that it refracted to, and you could figure out then, using Snell's law, what the index of refraction of this material was, and then even take the index of refraction of this material and plug it in and find out what the actual speed was of light in that material. Okay, the bigger of a change it is, the more it's going to bend. Okay, so it just takes a little bit of practice with those, and you get to be pretty good at them. But that's the basic idea of it. Next, we want to talk about the situation where we get something called total internal reflection. Okay, that's our next big thing here, total internal reflection. And I know we said we were talking about refraction, and now I'm going back to reflection, but they have to do with each other a good amount. So let's look at the situation where we have light changing a medium. Okay, here's our boundary. Here's our normal line. And we want it going from a high index or low speed, so high in to a low in. So that's low speed to high speed. This only works going from low speed to high speed, and that should make sense to you by the time we're done as to why that only works low speed to high speed. So let's take, and let's have our first ray of light. We're going to send it in about like this. As we just talked about above, a light ray going in like this will bend away from the normal. So it's going to bend it over a little bit. It's not going to go on that straight path, you know, that it was going to try and do. It's going to bend over a little bit. And then as we move our angle out a little steeper, it's going to bend over a little more like that. And as we bend this out a little more, it's going to bend a little more. And there eventually we'll reach a point where we hit this, we go in at this angle, and I'll make this line a little extra dark. It's going to go in at this angle, and then it's going to refract over to 90 degrees. That angle keeps increasing, and you see this is why this only works when you're going from high end to low end, because the other ways it refracts away from the normal, which means it refracts further and further from 90 degrees. But we're going to get it to refract to 90 degrees. If we keep going further, this keeps pushing over closer and closer, and it eventually will refract to 90 degrees. And it turns out that the angle where that occurs, this angle here, from there to there, the angle where that occurs is called the critical angle, theta critical. And that's a critical angle because what happens is, and I'm going to do the light in a different color, is any light beyond that, any light beyond, and now you have to be careful because maybe I shouldn't do this in a different color because I'm drawing it in a different color just so it looks a little better, but really it has to be the same color because the index of refraction is different for different colors of light. So I'm not changing from red to green light. So the critical angle for red light would be not the same as the critical angle for green light. But just assuming I didn't actually change the color of light, and I'm just doing this so you can see it a little better, anything beyond that critical angle gets reflected, totally reflected. There's no more transmission, and so it becomes known as total internal reflection, where this would be the incident angle. Oops, I'm sorry, that would not be the incident angle. So, my mistake. That would not be the incident angle. This out here is the incident angle, and then this angle over here would not be it would be the reflected angle. Okay, and those two then would be the same because it would act just like reflection. This is something you maybe have seen if you went underwater in a pool and you looked up at the surface of the pool, especially from the far end of the pool. If the pool's like this, and you go underneath the water over here, and you look up all the way over here at the top end of this pool, and you look at the top end of this pool, and on the surface of the water you see like a reflection of the wall or something, because the light would bounce from over here, and so you'd see this part of the wall. You can maybe do it with your watch if you have your watch face, and you tilt your watch face over far enough. This is my attempt to draw your a watch strap and everything. So you tilt the watch face over far enough, and then the light will be so steep that you'd be beyond that critical angle, and then the watch face looks like a mirror, and then yeah, I could finish it up there. There you go. It's their watch. Another place you could see this is you could do it probably with a cup of water or a fish tank. If you ever looked, you're looking at some fish, and you get down below it, and there's got your fishy and fishes in here, and you're down here looking at it, and you look up at that fish tank here, and it just looks like it's all glassy, like it's all made out of a mirror from underneath. If you've ever experienced, that's what that is. That's total internal reflection. This has some uses. One of the biggest uses is in fiber optics, and so the idea is that you can send light through some sort of optical cable, and it will bend around corners. So you could imagine if we had a fiber optic cable that had like some kink or something like that in it, it has some bend in it like that, and it's pretty neat if you ever want to look at how they make it. But if you send a light beam in, what will happen is this has such a high optical density compared to air that it pretty much always internally reflects. And so when it gets here, instead of the light just refracting and leaving your here, it hits and bounces off, and then bounces off and bounces off, and it basically just bounces its way, down the cable, and your signal doesn't get cut off, and you can pass it around and use this optical thing, and it'll bounce around and reflect around until it reaches the end of your little, your hair thin fiber optic cable, and you can communicate with it. But you have to have a really high optical density for that to work. But you can get the light to, bend, like with some quote signs, bend around the corners in that cable. The last thing I have to say about this is we've been talking about refraction and reflection, and we've had them as separate things, but you have to kind of keep in mind that really anytime a wave changes mediums, if it goes from, this is sound waves, this is ocean waves, this is any kind of wave that changes mediums, this is electrical signals, all kinds of stuff. When they change a medium, there is some transmission and there is some reflection. So some of the light will refract through and transmit, and some of it will be reflected. Now, depending on how big of a difference it is between these surfaces and what two materials you have can really dictate how much of it reflects and how much of it refracts. But essentially what happens is you send it in and some amount of it reflects. This would be your reflection, and some of it refracts. Okay, it could be more that reflects or more that refracts. It really depends on your materials and what angle you're at and everything like that in the situation. But technically speaking, this could have drawn that at a better angle that matched this other one. This is the reflection. Ignore that one for the moment. But you've got, the incident theta I, and you've got the theta reflected, and you're always going to have some reflection and then some refraction. And this is useful in things like your car mirror, like your rear view mirror. What you do is you have your rear view mirror, and they make the back side, so this is the mirror side that's silvered, and they put the glass on the front of it not exactly parallel to it. And so this is like a side view of your mirror. And then you have that little tab that sticks out on it. And so during the day, it uses the back side of this mirror. The light comes in here and it bounces off and goes into your eye over here where you're looking at it, right? Side view of your eye, right? So where you're looking at it, okay? And then, I know that's not the greatest eye, but whatever. And the light goes in that way. And then you flip this switch, and what it does is it moves this way, and then the whole thing kind of rotates. And then this non-parallel part becomes what you're looking at. So this back mirror part is no longer any light coming in and hitting off of that, is just bouncing straight out. It's not coming back to your eye. But the front edge where it's just glass, there's not a lot of a reflection from it. I'll do it in a different color. Now the light comes in and bounces, the light comes in, bounces off the front side of that mirror and goes into your eye. And so you see a lighter reflection. It's not so heavy, and it kind of looks almost like a ghosty kind of image of all the cars behind you. And then at night, when they have their bright light shining in your eyes, it reduces that reflection, and it doesn't hurt your eyes as much. So at least there's one little example of taking advantage of that reflection off a surface, off of glass. And you've seen that too. You're looking through like a store window and you see a reflection. You can see what's inside the store window, but you can also see your own reflection, a little bit like a ghosty, transparent version of yourself. So anytime a wave changes mediums, you get some reflection, some transmission. Okay? I think that's pretty much all.